Welcome. In this video we continue our discussion of components of the X-ray generators, and we're going to zoom in on transformers. We have already seen transformers in our general overview shot of the components of an X-ray generator circuit. We saw it with an auto transformer, that's a particular kind of transformer, and we also saw it with a high voltage transformer and a filament transformer. Now let's discuss what a transformer is. A transformer for our purposes and in general is known as a passive electrical device. This device, however, has the ability to change the amplitude of our voltage. It can change the amplitude of our voltage and also of our current. Because of this, transformers, or when I say change, I mean this device has the ability to transform the voltage amplitude from one value to another. It could lower the value or it could increase the value. But the point is, a transformer has the ability to change, hence transform, the amplitude of our alternating current signal. Now, transformers only work with AC signal, not with direct current. And a typical configuration with a transformer is that it has two coils. Think of coils as windings, a wire that is wound into loops. So typically in a circuit, a transformer will be represented by this symbol. Notice here we have a coil on the left and a coil on the right. The key here is that these coils don't have to be electrically connected. They actually need to be close to one another, and that's how a transformer works. But now you might wonder, how can this transformer signal if these two coils are not connected? Well, this has to do with the principles that a transformer uses to carry out its operation. Well, before we get into those principles, we need to set down some conventions. The side of a transformer that is connected to the power source, remember we have an AC alternating signal from the source, let's say from the outlet, our mains. The part of the transformer that is connected to the power source is referred to as a primary coil. Over here, because I don't designate which side is connected to the power source, I only label them as coil 1 and coil 2. Let's suppose the power source were to be attached on this side. Well, then this coil 2 would be our primary, and this side would be the secondary. Also reverse or conversely, if this side is where the power source were to be attached, then coil 1 will serve as a primary and coil 2 will serve as a secondary. Those are just useful conventions because they're quite meaningful. Okay, now let's consider, how do transformers work? What principle of physics is being employed here? Well, the principles involved in the operation of transformer is known as electromagnetic induction. And it is important here that we are inducing current. We have a source that is connected to one coil, and the other coil is not electrically connected to the source, so on that side, current is induced. Okay, well, let's review one of the principles we learned earlier, in particular in RPH 100. What we learn is that when we have a long conductor or a wire through which current is flowing, and typically the current has to be non-constant, when you have a current that's flowing through a wire, that current induces or generates a magnetic field around it. Flowing current through a wire, it produces a magnetic field around the wire. And the size of the magnetic field is given by this formula here. Mu 0 is the permittivity of space-time, or space. That's because electromagnetic waves travel in space. So mu0 is the permittivity of space, and I here is the amount of current flowing through our wire. 2 pi, those are constants, and d corresponds to the distance from the wire. If we're sitting d units away from the wire, this is the amount of magnetic field we will feel at that position, d units away from the wire. So this is quite a common, well-known fact described in physics. Actually, this is why a lot of people, at least recently, they have indicated or they have argued that it is not the electrons that carry electrical power or electrical energy, but it is the magnetic field, electromagnetic field around. And that is true. But you will notice that the the magnetic field is smaller the further you are away from the wire, and it is larger the closer you are. In other words, the larger the distance d is, the smaller the magnetic field that's going to carry the electrical energy. That's a little bit of a sidebar. The point is, for practical purposes, we can still think of the electrical energy as being concentrated around the wire. You might see people on the internet saying, well, the energy is not really flowing through the wire. That's true, but for all practical purposes, the distance d must be large. The larger the distance d, the further away you are from the wire, the less magnetic field, hence the less energy density would be in that point. But the closer you are to the wire, the more energy you would be, the larger the magnetic field, hence more energy. Okay, that's a sidebar. The point is here, a wire with electrical current generates a magnetic field. So there is a connection with the electric field to the magnetic field. A electrical wire carrying electrical current will have a magnetic field around it. Now, what happens if we make the wire into a loop? Well, the field strength changes. Not by a lot, but the magnetic field generated around that wire will look like this. You're welcome to use the right-hand rule to determine that the magnetic field lines will indeed take this form. But the point is that the magnetic field not only now depends on the size of the current, but it depends on R. R here is the radius of your coil, of your loop. If you make a loop of size R, that size of that loop will determine the size of your current. Another way of saying this is that the smaller the radius of the loop, the larger the magnetic field is going to be. However, not only does it depend on the current, that is, not only does the magnetic field, the induced magnetic field, depend on the current and the radius, but it also depends on the number of loops. N here is the number of loops. So this means we can increase the magnetic field produced if we made more loops. Over here we only have one loop, so N would be equal to 1. So this formula would be almost equivalent to this one. But the point is, we can increase the size of the magnetic field by making a larger number of loops. And if we make those loops very, very small, that is, the coil are tightly wound, we could also have an increased magnetic field. So the point here is we can produce a magnetic field from a flowing current. And the size of the magnetic field will depend on the amount of current, the size of our loop, times the number of loops we have. But then people have historically been interested. We know that current gives us magnetic field. Is it possible that we can generate, given a magnetic field, can we generate a current? Can we generate a current from a magnetic field? Well, it turned out it was true, and this work was by Michael Faraday and Lenz, that the earlier scientists. Their collaborative work produced or made it formal to us to understand how we can, given a magnetic field, produce a current. Faraday's law is more qualitative, while Lenz's law is more quantitative. And first of all, before I go to describing the two laws or reviewing the two laws, I would like to remind us of a quantity called a magnetic flux. A magnetic flux is just a measure of how much magnetic field is passing through a certain area. In particular, how much, remember, a magnetic field could be represented by the number of lines. These are the magnetic field lines. The more the number of magnetic field lines, that is a pictorial representation of a larger magnetic field. So flux is essentially the number of magnetic field lines passing through a given area. So if we have a lot of magnetic field lines passing through a given area, we will have a large magnetic flux. Now, we are ready to begin to talk about how a magnetic field could be understood to give us a current. Well, the work of Faraday and Lenz could be formalized in this sentence, in that a changing magnetic flux induces a current or a voltage. A changing magnetic flux induces a current. Another way of saying this is, if we had a bar magnet here, we would have a number of field lines passing through this area. So the magnetic field, there would be a certain magnetic field passing through that surface area, so we would have a flux. But if the bar magnet is standing still, that means we don't have a changing flux here. However, if we move the magnet through, notice the number of field lines passing through this area is going to change. And by virtue of that magnet moving, hence the magnetic field or magnetic flux changing, we will induce a current around this conductor. That is the qualitative and quantitative discussion of Faraday and Lenz's law. And I emphasize Lenz was the one who made it more formal quantitatively, and he derived that the voltage generated, or the potential difference generated in this conductor, depends on the change in magnetic flux exactly this way. That is, V, that's the voltage, is equals to minus the number of loops in your conductor. If you have no loop, then there would be no way to generate current. But if you have N is equals to 1, if you have one loop, then N is equals to 1. If you have 10 loops, N will be equal to 10. Now, that number of loops times the magnetic flux change, or the amount by which the magnetic flux changes with time, that gives you the voltage. That gives you the voltage. The details of this are a little beyond our scope, but if you like, you're welcome to post in the comments. I would happily talk about them in a different video. But the point is, if we have a magnetic field, a change in magnetic flux with time, that magnetic flux is going to generate some current or some voltage. And that voltage will drive flow of current. Now, this formula just rearranged, and this is for convenience later down the road. I've divided both sides by N. So we have V over N, that is the voltage generated divided by the number of loops, is equals to minus the magnetic field or flux, the change in magnetic flux. Now, Consider here a transformer. This is one configuration of a transformer. Remember, a transformer has windings, two windings or coils, and these coils, one of them may be attached to a source and one may not be, but the point is the two coils are not electrically connected. But in this case, we have a coil winding around a metal core. I emphasize a core. The purpose of this core is to trap or to contain the magnetic field lines inside of that core. The core here is typically made out of iron or a metal, and magnetic fields are they really like metals, especially that are ferromagnetic. Okay, so we have a coil here and a coil this side. Suppose we were to attach this side of the coil to a magnetic field, a source. The source will drive current through this wire, but remember, a moving current generates a magnetic field. So we will have magnetic field lines moving through these windings. So the pink lines here correspond to the magnetic field lines generated by the current flowing through this coil. But then, remember, the magnetic field lines are contained within this core. This means the number of the magnetic field will also pass through this coil. So if we had a magnetic field of a certain number of Teslas going through here, same thing would be true here. The magnetic field flowing through here must also be the same. Now, check. This side we have current flowing, and that current produces a magnetic field. But this side we have a magnetic field flowing through a conductor. Through a coiled conductor, or through windings of a conductor. That fact that there's a magnetic field flowing through a coiled conductor, means in this wire we will generate current. So the source produces current. The current flowing here produces a magnetic field. The flowing magnetic field induces a current on the secondary side. So although these two coils are not physically and electrically connected, but by being in the vicinity of the flowing magnetic field, the flowing current here eventually induces a flowing current here. Of course, it does so through the magnetic field. The main takeaway here is that the change in magnetic flux on the left side of the transformer must be the same as the change in magnetic flux on the right side of the transformer. That's how the magnetic fluxes compare. They have to be the same because the number of magnetic field lines flowing through this coil is the same as the one flowing through that one. If we have 10 magnetic lines per second flowing through this side, we must necessarily have 10 on this side. The point is, the change in magnetic flux on the primary side must be the same as that on the secondary side. This brings us to the first law of transformers. Remember from Lenz's law that the change in magnetic flux is nothing more than the voltage produced divided by the number of windings. Well, on the primary side, our voltage was Vp, and the number of windings is represented by N sub P, and P here means primary. So then we can equate this change in magnetic flux to this. And the same can be done on the secondary side. Unfortunately, my N sub S here, the number of windings on the secondary, is a bit in the obscure region, but the point is the number of windings on the secondary side is represented by N sub S. So this means the change in magnetic flux on the secondary side must also be equal to minus the voltage on the secondary side divided by the number of windings on the secondary side. But remember, these magnetic fluxes are the same. So we can happily equate these two ratios, leading us to arrive at the first law of transformer with regards to voltages. The law of voltages with regards to transformer is that the voltage on the primary side divided by the number of windings must be the same as the voltage on the secondary side divided by the number of windings. Okay, that's a lot of theory. It's time to put it into practice. Let's see how this looks in practice. Well, here we have a portable X-ray unit in this example, and it has a step-up transformer. The 120 unit, so this X-ray unit is hooked up to a 120 volt source, but it needs to transform it or change it to an amplitude of 100 kilovolts. That's what the X-ray machine or the X-ray tube needs. It works with 100 kilovolts, but the source only has 120 volts. So this is where we can use the law of transformer with regards to voltage. We can amplify or increase or change the amplitude of our voltage. Well, how will that look? Well, first of all, we're told that the number of windings on the primary side is 50 loops. So we have 50 windings, and we are required to find what is the number of loops in the secondary side in order to achieve this amplification. Well, let's put everything to the test. Let me increase the size of my pen. So we have V over VP times VP over VN, NP equals to VS over NS. We know what VS is supposed to be. This is supposed to be 100 kilovolts. We are interested in NS. It is the number of loops on the secondary side that we are ignorant of or we'd like to determine. We know what the input source supplies. It supplies 120 volts. And we also know the number of loops on the primary side of our transformer. So this is 50 loops. Therefore, we're able to determine what NS is going to be. NS is going to be VP over that is VS. I'm sorry about that. Let me quickly, I'm almost making a mistake now. So NS is equals to VS over VP times NP. We know the values, so we can punch them in, and I would like you to post your findings in the comment section. In the comment section, put in example 1A, NS equals to, you could punch it in there. So we could, if you have trouble, then I'll know. Okay, so VS is 100 times 10 to the power 3 because it's kilovolt, divided by the VP is 120 volt. So that's volt times 50. You will notice that the number of loops will have no units. So up to you to find. That is your part, your contribution to the video. That is, in the comment section, tell me what you find. Okay, now let's step back. This sounds like scientific magic where you are able to somehow take a weak source, battery or whatever source or AC signal of 120 volts, and somehow you're able to get it to 100 kilovolts. If we could do this, man, we won't have any energy problems. Well, in nature, there is no free lunch. If we are increasing the amplitude of our voltage, we must be losing something elsewhere. There is no way that we can just increase the amplitude at no cost. There must be a cost. Where are we losing? What is it that we are losing? Where did we pay the price? Where will this come and bite us back, so to say? Well, let's review something about electrical power. Electrical power is given by the current times the voltage. That is the power flowing through an electrical device. If you know the voltage of your across that device times the amount of current flowing through, you could tell me how much power is flowing through there. Remember, power is just the amount of energy per second. That's all there is. That's what power is. Actually, it turns out, if we take this observation, we can deduce what is it that we've lost at the cost of gaining a higher voltage. Let's, for this purpose, assume our transformer is ideal, so it is 100% efficient. There are no resistances, there's no loss, there are no inefficiencies. So we can boldly say, in this transformer, whatever power we've pumped in here must be the same amount that's flowing out through here. The point is, power in must be equal to power out. But the power in is equals to the voltage across the primary side, the voltage times the primary side multiplied by the current through the primary side. And the power out is going to be the current through the secondary side times the voltage on the secondary side. Remember what Vp and Vs are. If you were to make this ratio a subject of the formula, you can arrive at this law. This law here is the law of currents for transformers. Remember, the first one was the law of voltages. This is how the voltages on the primary and secondary side relate to one another. But we hadn't said anything about the current. Remember, the power here is the same and the power is the same. We know the law of voltages. What is the law of currents? Well, the law of currents through a transformer takes this form. That is, the current on the primary divided by the current on the secondary is equals to the number of windings on the secondary divided by the number of windings or loops on the primary. Let's check. Let's use our old example, the one we just did, to test this law as an example. Well, remember, we had determined, okay, I think this will lead me to some trouble, but I think we'll use it as an exercise. So the law of currents looks like this. Is, this is Ns over Np. This number you need to determine and post in the comment. Let's figure out what is the current on the secondary side. In this problem, they've given us that the primary side has a voltage of 10 amperes. 10 amperes. So on the primary side, we have IP is 10 amperes. And we know that NP, that is the number of windings on the primary side, is 50. Ns, that is the number of windings on the secondary side, you are going to determine. So for this, I'm going to use a question mark. Now, once you've obtained this, determine what Is is going to be. That is the current on the secondary side. You will observe that the current on the secondary side is going to be less than the current on the primary side. Let me reshuffle this formula so that to streamline things for you. This is going to be Np over Ns times Ip. Ip is 10, Np is 50. This is to be determined. So also in the comment section, post what you find. You will notice that the current in the primary side is larger than the current in the secondary side. Remember what we learned from the voltages The voltage on the secondary side is larger than the voltage in the primary side. The point is here, by changing the voltage, we started off with a small voltage of 120 and we've increased it to 100 kilovolts. That's why the secondary side has a larger voltage than the primary. The cost of doing so is that the current on the secondary side is much less than the current on the primary side. So we didn't really gain energy out of nowhere. We just traded off. By this, you will observe that any transformer that amplifies the voltage, it actually reduces the current. And any transformer that amplifies the current, it will reduce the voltage. This then enables us to classify transformers. Okay, before we get to the classification of transformers, I would give you this third example. In this example, I would ask you to calculate the power in, having determined the current on the secondary side and the number of windings also on the secondary side. I request of you that you calculate the power in, that is the power on the primary side. Compare that to the power on the secondary side, that is the power out. So remember, this is going to be IP VP and this is going to be IS VS. Post your findings also and tell me, are these different? Are they equal? Is one larger than the other? You will, I guess I'll have to jump the gun in order to make my point. You should find that the power in must be equal to the power out. Because if you're dealing with an ideal transformer, a transformer is passive. All it does is it does a trade-off. It can amplify the amplitude, it can amplify the voltage, and at the cost of the current, or it could amplify the current at the cost of the voltage. But the point is the power output must be the same as the power input. Okay, now we are ready to classify transformers. Anytime we observe, by the way we classify transformers is by using what we call a turns ratio. This is what a turns ratio is. It is the number of windings on the secondary part of the transformer divided by the number of windings on the primary side. This is what we will call a turns ratio. Some books, some texts might use the reverse or the inverse of this, but for our purposes, when we mean turns ratio, we mean secondary over primary, the windings. Now, a step-up transformer, a transformer that increases the voltage or that amplifies the voltage, will always have a turns ratio that's larger than 1. In other words, the windings on the secondary side will be larger than the windings on the primary side. Whereas a step-down transformer will have windings, the turns ratio will be less than 1. Hence, the number of windings on the secondary side will be less than the windings on the primary side. There is another kind of transformer that is an isolated transformer. This one has windings that are similar. They are the same. The number of windings on the secondary side is the same as the number of windings on the primary side. This is useful for safety purposes. In case the side of the circuit that is connected to the power source has fluctuations or is shorts out, the secondary side of the circuit will be unaffected. At least the electrical shock will not be transferred to the electrical short circuit will not be transferred to the secondary side of the transformer. Because remember, these transformer, the secondary and primary side are not electrically connected. Only the current is induced It is produced or generated by the changing magnetic flux. Okay. Now we come to a special transformer. It is special because it can change its property based on how it's connected. This transformer is called an autotransformer. It is a tapped transformer. What this means is that it has multiple terminals where you can close the circuit or where you can make connections. And where you close or where you make connections, at least on the secondary side, changes the characteristic of the transformer or what role it plays in that circuit. The point is, it's versatile. It can work as a step up, a step down, or an isolated transformer. So its function depends on how it's connected. This might seem very complicated, but let's get our hands dirty. Let's get our hands dirty. Here I have a typical picture of an autotransformer. Notice here we have an AC signal. This is an alternating signal, so this is the source. And you will notice that there is a coil here. This coil represents an autotransformer, and it has multiple taps on the secondary side. That is the points where you can make connections to the secondary part of the circuit. Now, if you have a voltage on this side, the number of windings on this side of the circuit is going to be the sum of these 7 plus 3 plus 3 plus 3 plus 3. That is the number of windings we will have on this side. What is that? 10, 16, let's say 19. So the number of windings on the primary side is 19 windings. But how many windings do we have on the secondary side? Well, the secondary side depends on where we have made our connection, where we have closed our circuit. Notice we've closed our circuit on this second tap, the H tap. I've designated this tap with letter H. Well, how many windings are on this side of the circuit? Well, it's 7 plus 3. So in this particular case, we have 10 windings on the secondary side. Now, how would we classify this transformer, the autotransformer, in this particular configuration? Well, notice the number of windings on the secondary side is less than the number of windings on the primary side. Well, how do we classify that? We classify it as a step-down transformer because the number of windings on the secondary is less than the number of windings on the primary. So, in this particular configuration, the autotransformer is serving as a step-down transformer. Okay, now let's take another example. Suppose we conclude the tap, or we close the circuit in tap number, or tap labeled F. Our label here is F. How many windings are enclosed here? Well, we have 10, 16 in total. 16 in total. That's 16 taps, and we have determined that on this side is 19. Notice, how do the number of windings compare from the secondary to the primary? Well, these guys are still less than these guys. So this autotransformer still works as a step-down transformer because the number of windings on the secondary is less than the number of windings on the primary. Let's change things up, for instance. Now, in this configuration, how would you guess that autotransformer would work? Well, unfortunately, this is asynchronous, but the number of windings again on the primary side is still 19, but on the secondary side, the number has changed. It's not 19, but it's 19 plus 2. So the number of windings here is 19 plus 2, and this will give us 21 windings on the secondary side. Therefore, in this particular configuration, our autotransformer works or functions as a step-up transformer. the voltage we expect to observe here is going to be larger than the one in the source. Okay, I believe that should be clear, but let's do one more example. What would happen if we had made a connection onto tap E? We had closed, or we had closed our circuit on tap E. Well, notice the number of windings on the primary side would be exactly the same as the number of windings on the secondary side. So the autotransformer here would be functioning as an isolator transformer. An isolator transformer. Okay, I believe that discussion is good enough for our purposes. If you have any questions, you're always welcome to post them on the comment section. This discussion should enable you to attempt these exercises in our book. And I will stop here. I will see you in the next one.